So let's get started. So today the goal will be going over the estimation, but before that, let's very quickly review what we have been covering in the sampling distribution, because we actually would be using the result we learned, which we said is rather boring results, but they will be very useful. Okay, so the main thing we need to recall is the meaning of population sample. The idea is that population will be the one we want to study, okay? But we can only study part of it, which is called the sample, because we are never able to collect all the data, right? So we only able to get it, and then we want it to be representative. So one way to consider a sample is called a simple random sample. And from that, we are looking at what we call statistics. It's a function of the random sample, which is a random variable, right? The example is sample mean and sample variance. Today, we'll talk a little bit more about that. And in particular, we study the sample mean because this is the main object of study for our class, okay? And to remind you that it's a random variable, okay? And that's the reason it's a random variable. We understand how the mean looks like, how the variance looks like, right? And we know the expectation of the sample mean is same as the original population mean, right? And the variance of the sample mean is directly proportional to the underlying variance, but inversely proportional to sample size, right? Because the sample size larger, your sample mean will be more informative. You have higher precision, right? And when n goes to infinity, right, there's no more variance, right? That what it means is here, right? There's when the law of large numbers said when sample size get very large, okay, the sample mean will be very close to the mu, and there's no more uncertainty there, right? It simply means you get bigger sample, okay? The sample mean will almost always exactly at mu, okay? Or very close, okay? And we have another one is, although we know there will be no more uncertainty, but how still, right? There's some probability, right? Unless you go to infinity, right? And even before that, I mean, how would the distribution looks like? And we don't know when n is small, but we always know when n is big enough, then it's a bell curve, okay? So that will be one of the main key things we use in our class to remember. This one is the sample mean will follow a bell curve, okay? So that will be the formula. Actually, later we'll see today will rely on this fact, okay? The sample means a bell curve. And do remind you that central limit theorem does not need the underlying distribution. It's a bell curve, okay? So that's a second thing. And next is about binary data. And there's nothing special about binary data except the fact that you can see the mean and variance are related, okay? Once I know the mean, I know the variance. So that is the very important property of binary data because of the binomial distribution. So when I know the mean, I know already know the variance, okay? So same for sample proportion and the variance, okay? And central limit also applies for that case, okay? So lastly, this is also we will talk about today, is if we know sigma, then that's fine, okay? I mean, we have some good estimate of sigma, there's no problem. But what happens if you don't know? If we don't know for sure, or if you could estimate, that will be fine. But if you don't have good estimate for sigma square, then we have to rely on S square, okay? Which is a sample variance. But when the sample variance comes a problem because of this guy, how does it look like? It's not clear because central limit theorem doesn't apply, right? Central limit theorem requires to know the sigma, and we can't really apply directly. And it has been shown, okay, this guy, okay, turn out to be, okay, if you assume the underlying is a normal, so that's very important. Assume underlying is normal, okay. Assume the population follow normal, then this guy will follow a T distribution, and the T will be a bell curve, a normal bell, which have a fatter tail. And how fat the tail depends on sample size. And the larger the sample size, the tail is thinner, right? And you probably remember for T distribution, when n go to infinity, it's exactly the bell, right? So it's exactly the normal bell. So that is the idea, okay, behind this one. And you can imagine when n is big enough, actually the bell curve will be no difference, because for the T distribution, when n is more than 100, okay, actually there's not too much different from this T bell and the normal bell is very similar, okay. So that's why in a lot of application, we just being lazy, just when have n is big, then just apply the standard bell, because they are so similar. This is just a minor adjustment, okay. So that would be the key from this lecture, okay. So we'll go to the one that we talked today, okay. And do note that all these are just facts, you can imagine, because I'm not proving anything. There's some fact. I try to explain, but there's some fact there. And we'll use this fact for our class, okay. But they are basically the basis for the rest of the semester, okay. And now we're going to topic A. So before I go to topic A, I would like to announce one thing is we will move the next Wednesday. We don't have class because I move it to the optional tutorial for our studio at the end of semester. Okay, I will move one more class, but I'll announce later. But next Wednesday we don't have class. We'll be rescheduled to the lab again because same the Python. We do the Python in the lab. So and our studio we need to do a lab. So no more class, no class on Wednesday. I will announce in the Blackboard as well. So you will have an email, but there will be the class on Wednesday will be rescheduled to the B.A lab, or reschedule another one because the B.A lab is a 3-hour class, so I will have to move another one as well. But I'll let you know once I know the dates. But very likely that there will be the Friday afterward. I'll put that on the Blackboard. So today the goal is to finish estimation. As you can see, the slide is not a lot, so we should be able to finish them because you notice from now on it's more like you know all the thing. There's nothing new here. So if you understand what we have covered, so we just apply them. So that's not really something big. Okay, there's some more concept, but shouldn't be a big thing. But this topic estimation would be probably one of the most important thing, right? Because we collect data, and one of the things is want to estimate mu. Right? Remember the question of I want to know in China. Suppose I have start a new business. I'm Elon Musk. I'm having a new smartphone called X phone, right? That can cost $1 directly. Then I want to know how 1.4 billion people, how much they want to pay, right? And of course, you can ask 1.4 billion how much to pay, then you're done, right? But the problem is it's difficult to ask. 1.4 billion is very expensive. Then what we're going to do is to ask some group of people, that's called a sample, right? And you ask them and try to hope this is, if you draw the sample in a random fraction that is going to be a nice one, then the sample will be representative. But what you learn from the sample will be able to carry forward to guess what is happening in 1.4 billion, right? And so the question is like, I want to estimate the average willingness to pay, right? Then I can say how to price the product, whether I should sell it or not, and how much money to spend, right? So then we require estimation, right? We want to know the population parameter mu and sigma square, right? Just go back, maybe just try to draw a picture to kind of idea, right? Because the idea is like this, right? Always you want to have always a population which has so many people here, we are unable to have chance to talk to everyone, right? And the thing we care, there are many things we care, right? The population is so large, 1.4 billion, right? There's no point to know every single aspect of the population or what's going on, right? So when you learn topic 1, you know something we care. The first thing we care is sample mean mu, right? Population mu, right? The average willingness to pay for your phone, right? And also the sigma square, okay? These are the two things that is we call summary statistics, right? If we know everyone here, then it's good, right? But if you don't know, then what we want to know is the two things, right? From topic 1, you know, is the mean and the sigma, right? Variance, right? Population mean and population variance, okay? And today we're going to talk about how to estimate them, okay? And we'll talk about how to estimate mu and sigma square, okay? But we focus on more mu, okay? We talk about a little bit sigma square. And how do we know this one, right? Estimation means that I suppose I got some sample here, okay? Sample here. Okay. And from the sample, I have x bar and s square, right? Remember, x bar is just sum of the data over n, right? Remember, this is a random variable, right? Because it depends on which sample you got, but once you got a sample, then they are no longer a random variable. But still, this is the way we try to estimate, right? And this is the way we try to guess, right? So we try to get x bar to guess the mu and s square to guess sigma square, right? So it is the very practical subject, right? It's because we want to know mu and sigma, right? Because that's a way to describe the population, right? The things, the so big object we want to study. And the way to achieve this is to use these two, okay? First, we will say why they are the good one, okay? Why they're good one. We give you some property why they're good, okay? And to have a guess on mu and sigma, right? There are two ways to do it, okay? One way is just to guess a number, which we call point estimate, okay? We just give you one number, that is a point estimate. And the other one later we will see is called interval estimate, okay? We don't give one number, we give bunch of number, okay? That's exactly the same as you look at the news in the morning. They ask the expert, okay, what is Hang Seng Index today, okay? If that guy say, today the stock market will be 17,000, okay? That will be his guess. That's one number, point estimate. If he said will be within 16,000 to 18,000, okay, give you a range, then it's interval. Okay, later we will see, but this is a graph that we are trying to look at. Okay, so we try, that is overview today. Okay, I hope it will become clear as we go through the slides. Okay, now, so here we have to make some terminology, but shouldn't be a very deep thing. We'll call parameter. Okay. Is called the variable that interesting in the population. Is often, as I said, we care about mu and sigma square, right? That's the main thing. Of course, you probably in your mind probably also maybe I should care. Maybe I will care the range, IQR, kurtosis, skewness. They're all parameter. But in our class, we elementary, we focus on mu and sigma square, and mostly mu. But sigma square looks slightly a little bit, but mainly. And usually in the notation, we will use theta, the greater theta, to summarize them, okay? And average, as I said, is the thing we care most, okay? Now, here's another terminology we call estimator, okay? Estimator, because this class of estimate, right? So I have to guess what's the parameter, okay? And estimator is the way or the rule of thumb of the function to guess, how you guess, okay? An example is what we have, sample mean, right? Sample mean is the main way to guess the population mean, right? X bar is the way to guess mu, right? S square is the way to estimate sigma square. And the way you estimate is called estimator. And the way you estimate is called a function, right? So, and this is actually statistics, right? Statistics is a function of random variable, okay? But if you used to estimate parameter, that is called estimator. So the difference between statistics and estimator is the last three letters to estimate parameter. Okay, if you're not estimating anything, just some statistics. Okay, just some random function or some random variable, right, of your random sample. Okay, but now we are a function of the sample that estimate parameter. Okay, so whenever you want to estimate something, the function, okay, is called estimator. Remember, estimator is a function, so it's the way to estimate. Okay, and of course, by construction, this is a random variable, right? Because it depends on the sample you got. Okay, the value would varies between sample and sample. That's called estimator. Okay, and that means if you collect your data, okay, and comes up with a number, you plug in, then it becomes estimate. Okay, estimates exact number you have. Okay, for example, estimate is 5. Okay, estimator is sample mean, is the way you calculate it. Okay, it's very simple, just some terminology. I put it there because every book have to define like this way. I mean, I don't think it's very useful for our purpose, but for those who want to study further, you have to know terminology. Otherwise, you will confuse, because you have to distinguish very carefully what's random variable, what's a function, what's exactly a value. Otherwise, no one knows what you talk about. But actually, for our purposes, yeah, for business application, it's okay. But I guess it's good to know at least the terminology, right? I mean, I'm not trying to ask you in the exam or the assignment what is the definition of difference between estimate and estimate. No, I'm not going to talk about it. Don't worry about it. But you should know. I mean, why they're different? Because otherwise, other people use it. You should know, right? It's not about I'm trying to make you differentiate what is what, right? But I have to emphasize. Otherwise, you don't really know when other people talk about what's estimate, what's estimator, what's statistics, right? What's a sample? What do they mean? But I hope it's clear. Okay. And as I said at the beginning, what is estimator? There are two types, point or interval. Point, I'm just guessing one number. Okay. And interval is I try to give a range. Okay. So for example, maybe you're trying to guess how old I am. Okay. Or how old that beautiful lady was, right? And if you try to guess, right? Suppose your girlfriend or your mom, okay, ask to guess how old she is, right? The standard answer is either 18 or 25, okay? Only one answer, right? You're not going to guess otherwise, right? And if you try to guess what is my age, right? Then probably you might guess from 30 to 50. Then might be a reasonable guess, right? I mean, of course, you can smaller the range, but you can't. It's not easy to exactly pinpoint, but you will probably give a range. Or as I said at the beginning, right, to guess what's the Hansen index, right? If I give a particular number, maybe today's stock Hansen index is going to be 16,532, then unlikely that you will believe him. But if he say it's between 1,600 to 800, then probably you would have something to say, right? And as I said, either you give a point estimate or interval estimate, right? Okay. So and then you notice there are two different things, okay? But it will be clear, okay? How this being done. Don't worry, they're very mechanical. So just you do enough exercise, then you know what's going on. So it's nothing very difficult. Just you see this is the rule. You see this is the rule. It's more like accounting practice. So I would say, I mean, it's very simple. Okay, it's maybe boring, but I try to give you the idea why this is true. Okay, because the rule is rather simple. Okay, the formula is very simple. Later you see if you read the slide, then you know already. But the rule is very simple. But I try to give you the idea why they're true. Okay, I mean the key point of this class is why they're true. Because all the formula is there, the slides. I mean, you don't have to attend the class, but you attend the class because you want to know a little bit more, right? Of course, I take attendance as well, but that is a minor point, right? Compared to the time. So as I said, if financial analysts give you one target point, there's an point estimate. If you give above no bound, then it's called interval estimate. Okay. So point estimator. So actually, the in statistics, it has been argued, well, generally accepted there's a three nice property. If we want to guess one thing, what would be best guess, right? Suppose you ask me, okay, as I said, right? And I guess age of a beautiful lady, right? I always said 25, regardless of how old it is, right? Is this a good rule? Okay. I guess so, but I mean, why is a good rule, right? You have the good rule, you have to unbiased, efficient, or consistent. Let me define properly, okay? For unbiased, okay, I think we have seen that actually this is the property of sample mean, okay? Unbiased actually means if I have to repeat this process, which we never do, but suppose to repeat it, okay? You repeat many times, okay? And you average out those outcomes, actually uncover the truth, okay? That means on average, you hit the target. So look graphically, what does that mean, okay? It means the following, okay? Suppose in one sample, this is what we got, okay? And in other case, I got this guy. And in other case, I got this guy, okay? Although none of it close to the target, okay? But average of them is the target, right? So at least there's some hope that if we are to repeat what we are doing, okay? And it should enable us to get what we want, okay? So this is somewhat we call a minimum requirement, okay? Sometimes we will say, okay? Of course, in machine learning, if you study more, then this is not will give up this goal, okay? Indeed, machine learning, a lot of the rule that you learn is biased, okay? But in a classical approach, we will favor unbiased estimator, okay? The reason is being that, I mean, we're thinking at least there's some hope. If you're to repeat the survey multiple times, the average of those is getting what we want, okay? And this is a classical criteria for that, okay? And that explains the reason why, later we'll see, we use the X bar to estimate mu, S squared to estimate sigma squared, okay? Why S squared is n minus 1, not n, okay? We don't do it to prove, but actually that is the theorem. I think it's somewhere the slide in the back, is to show we can show the expected S squared is sigma squared, okay? So that is the reason why we insist on using this instead of n. So that is the first reason why unbiasedness or on average hitting the target is important, okay? And as I emphasize, this rule, if you learn machine learning, we would be dropping this requirement, right? We will allow some bias, will be fine, okay? As long as you do some prediction is good, okay? But for estimate, precision is important. For prediction, sometimes it's okay, because for prediction, it's always machine learning is prediction. For prediction, we are able to drop this assumption. But anyway, this is a very important for estimation. So the next one is called efficiency, okay? And I have two estimators, okay? Both are unbiased, I mean, on average, a hidden target. And which one to pick? I picked the one with smaller variance, okay? The one with smaller variance is efficient, okay? And that is the accuracy of our hit. So, so you can see we have the A method and B method. A method actually doesn't hit the target, B doesn't, but on average, A and B hit the target, right? And A is closer to the center than B, right? In terms of variance, right? Because variance measures distance, right? So that means A is better, okay? And you probably why I mentioned this guy, okay? That is the reason I mentioned this is because variance, I mean, this efficiency, I didn't want to do the proof, but it explains why we use sample mean to estimate population mean. Because I don't do the proof yet because it requires some inequality, causes one inequality, but you show that if you look at other way of doing mean, like weighted mean, okay, or other types of mean, actually sample mean is the best, okay? So that's why we have been using sample mean to do it. It's not because sample mean is similar to population mean, right? But this is what we have, right? I mean, you can imagine if some value appear more often than other, you may want to give more weight, right? Suppose you roll a die, right? You don't know it's fair or not, right? If, say, you got a die, 3 and 4 appear more often than 1, 2, and 5 and 6, right? Probably you want to give more weight to 3 and 4, right? More proportional to their relative frequency, right? Then you want to use weighted average or some other method, right? And we can show, okay, at least in this case, right? If you consider linear estimator, okay, which is linear in terms of the what we have is sample mean is good, okay? So so that's why we've been using sample mean, because sample mean is estimator that is unbiased and efficient, which means it's accurate, okay, on average, and also the variance is the accuracy is good, okay? It's on average the target and good accuracy, okay? So that's the idea. And there's another rule, okay, which is more complicated. It's called consistency, okay? Which efficiency, as we said, right, is saying, sorry, F unbiased is on F hidden target, right? But it need not be the target, okay? Consistency implies when N is very big, it is hitting the target directly. There's no more variation. So suppose I have very big sample size, okay? And that is exactly what we want, okay? So that is the idea. The idea is like the graph is when sample size 1, it can be somewhere else, okay? Can be biased. 2 can be here, can bias. 3 can bias, but doesn't really matter bias, but at the end it hit here, okay? At the end, it is getting closer and closer to the target, okay? That is what we want. If you recall, law of large number, we imply this property, right? Law of number said when X bar is getting larger and larger and larger, it will be exactly mu, right? So here's what we want, okay? And consistent estimator, consistency, right, is a property that is also very good, okay? And either sometime you need to consistency, or at least you want some unbiased, right? At least one of them have to be true, right? Because either you have a very large sample size, you get a target, or you repeat this sample, we also get on average get a target, right? Otherwise, if you are not having either of those, then you're not doing the right thing, right? Because at least hypothetically, there's some way to achieve the target, right? That would be the case, okay? So now we give you already explain this graph, okay? I hope I give you the idea why this is good, okay? Using X bar to estimate mu is a good one because it is unbiased, it's efficient, it's consistent, okay? Unbiased, again, means on average hidden target, okay? If we hypothetically repeat the process, do many sample mean, but which we don't, but anyway, suppose we do it, on average hit it, okay? And it has small, it's efficient, it's a small variance, okay? Hitting the target without missing too much, okay? And it's consistent, it means that if we increase the sample size a lot, okay, we will get it, okay? So that is a good estimate, right? and S squared, okay? Although we don't mention it, we don't prove it, but it is also a unbiased, okay? And it's also consistent, okay? We don't want to talk about other, but that is we talk, okay? That's the thing we up to. Is that clear? Okay. So this is just conceptual thing because I'm able to show the proof because that's why there's no example here, and we just give the reason why they are true. Okay. It's not something that you'll be using. Okay. Because I mean you're already using it already, right? So I'll just tell you if you want to guess what's mu and sigma, you get the data. Okay. Guess what the mu and sigma is supposed to remember the leading example. You are hired by Elon Musk to say how to set the price of his X phone, right? Then you get the data, okay? And then you get the sample mean, you get the sample variance, then you can report to him. This is my guess on the mu, this is my guess on the sigma square, okay? And he should be happy, okay? Is that clear what you're doing, okay? You have a way to guess, okay? And this explains why in topic 1, we have n-1, not n, because the n1 is biased. Okay, but n-1 is not. So we want on average hidden target. So that's why we have the n-1. Okay, for the proof, I don't want to prove, but if you want, you can read it. It's not something super mathy. You'll be something like 1 page of slide of proof, 2 page slide of proof, and 3 page slide we can prove it. Okay. And I used to go over that, but I guess I spare you with this because, I mean, even though you look at it and then it's not going to make any insight from that, and you still use what you're doing. Okay, if you a QFN student or student who want to study further, they should have read that. Otherwise, don't bother. Is that clear? Okay, so I guess it's the time to go to the next one. Okay, binary data. Okay, for binary data, that is nothing new, right? You may ask, okay, because just CO1, right? And what we have discussed should be everything carried forward, right? There should be nothing new, okay? And so sample proportion will be an unbiased, efficient, consistent estimator. Nice property there. So that's nothing new, right? So that is, say, if I want to guess how many girls in CHK as undergraduate student, right? And what we're going to do is to collect a random sample of students and just look at the sample proportion. What's the percentage of female in my sample? Then I get a good estimate of the overall number, the percentage of female in CHK. That's very simple, right? Nothing new there, okay? Why I still talk about this is because of the fact how to estimate variance, right? Because remember, variance, okay, in binary, right, it's slightly different, right? In the binary data, right, the variance, right, is actually the mean times 1 minus mean, right? And how can we do estimate for the sigma square, okay? And what should be done, okay? And can we use this guy, okay? You notice most of the book use this one, okay? And you would, some of you, if you are mathy, you would jump up and say, okay, wait a minute. This is bias. Yes, this is bias, okay? But the one is not biased is this guy, okay? You have to adjust like what you do for the sample variance, okay? You adjust, multiply, and you probably ask, okay, why I'm using the biased version, okay? One reason you read the book, you will notice is n is very big when you do this kind of estimation because you ask yes or no, okay? And when n is very big, this guy, n over n minus 1 will be very close to 1 anyway, right? Because you do whether people like curry food or neither thing is more than usually at least a few hundred or even a thousands. And this thing will be close to 1 anyway. So there's no harm to use that. I mean, but of course, if you are super conscious, super worried, you can use this formula. But in the real world, I mean, as far as I look at all the application, people just use this guy. Okay. And just a technical note is why this guy still accepted. Because this guy, what we call, there's a property, what we call is called the asymptotic unbiasedness. Okay. This guy, there's a even weaker property called asymptotic unbiased, which means that the bias will go to 0 when the sample size gets very large, right? So that asymptotic unbiased means the bias is gone anyway. So when n is large, and we always use very large sample anyway, so that the bias is not a big deal, okay? But I don't want to talk about that because it's very. If you go to stat, you would learn it in the elementary level, but we are not stat class, so I just leave it there. Okay. So anyway, if you pick up any introductory stat textbook in business, they just give you this is what they do. I mean, they don't ever justify why we use this because we are being lazy. Okay. And since there's no difference, though, we don't bother anyway, right? Because when using binary data, usually you have more than a few hundred. And you have a few hundred, then your adjustment, does it make a difference? Usually no, right? It's n over n minus 1, right? 300 minus 299. I don't think that make a difference anyway, okay? Because it's not big. Remember the reason why I allow this to happen, but I don't allow this to happen because this guy can be very large, right? And this guy's large, and you don't adjust, then can be an issue, right? So that is the reason why we don't allow that happen. But we allow this happen because you can imagine, right? Because p times 1 minus p is not big, right? You multiply, doesn't really make a difference, okay? So that's one of the reasons why we're okay with that, okay? So to remind you, there's some bias here, but we just still use the bias one, okay? But it's not a big concern because pi is so small. We can lazy, then we are lazy, okay? Okay, so this is to estimate the variance, okay? Do note that S is p over 1 minus p, right? So we are not adjusting, okay? Okay, here is done with the point estimator. Okay, is that okay? I think I didn't give you any new thing, but just to probably you might have already guessed this is the right way, but I give you the reason why they're right. Okay, why you're using what we're doing, and then we just give the reason why it's n minus 1. Okay, as I promised in topic 1, we have to explain why they're right. Right? Now, I guess it's a good time to talk about the next one before break. Okay, I will give you the idea what we are doing. Okay, we'll justify that. Okay, interval estimator. Okay, so and we will no longer talk about variance. We just focus on the mean. Okay, we're gonna focus on the mean. As we said, right, to estimate the population mean, the mu, we would use the sample mean x bar. Okay, x bar, and we know x bar is a good one. Okay, but as I said, you give me one number. Okay, actually we don't use all the information, right? Because how precise x bar is, remember the formula, x bar is like this, right? It's like it's from this guy, right? Central limit theorem tells us x bar, okay, has a normal distribution like this, okay? And if suppose in the first case, suppose we have sigma, we know sigma square, right? And actually we have a better idea, okay? We can use it better, okay? Why? Okay. Let me draw a graph, okay? Central limit theorem tells us the following. X bar has a distribution of mean mu, is a bell there. Okay. And we have sigma square over n. Okay. Remember, it's not sigma square, but sigma over n, because depending on n, then the shape change. Okay. That central limit theorem tells us. Okay. Central limit theorem. Let me write that down because to emphasize CLT. Okay. And we got a sample. Okay. And we estimate. Okay. And when estimate, maybe we got here, right? We got here. This is a particular estimate. Okay. Okay. We got X bar. Okay. And that would be the best guess for mu. Okay. The question is, can we do more? Can we do more about that? Okay. And the idea is not to guess one point, but guess more. Okay. We want to go left by what we call M and go right by M. Is the, if you remember, one famous movie in the 90s called Titanic. One of the famous is I'm Flying, right? Just you have to scratch out the hands there and to fly, okay? And X bar minus M and X bar plus M, okay? And what we want is to stretch out from X bar, because X bar is a good estimate, stretch out from that, okay? And we want this, okay, to include mu, okay, as most likely as possible. Okay, we want a high probability that we want to include mu. Okay, of course, we can never include mu because it's normal, the bell is infinity, right? So we want a high probability. Usually we want, say, 90%, 95%, or 99% that include mu, right? And if you recall, right, the rule of thumb, right, you just add 2SD and minus 2SD. That is the way to go, right? You basically M will be just 2SD, right? 2 of this guy, right? Or 3 of this guy. Okay? That will include most of the thing, right? So that will be our interval estimate. Of course, we make more precise how to get 2 or 3. I mean, this will be a rule of thumb, but we'll get more precise there. We'll often use the 1.64 and 1.89 instead of 2 directly. But I will make more precise there. Okay. Just to remind you again before we break, we'll give more detail later. Is to repeat this graph is X bar is our best guess if we just allow us to give one number. Okay. But if you allow to give more than one number, how are we going to think about that? The number, right? And this number, okay, I want to extend left and right, okay? It's a range, right? Okay. And I want to able to capture the mu with high probability, right? I want to capture it, okay? So I go left and right, and the logic is remember under the bell, right, is everything within 2SD or 3SD. Remember the rule of the thumb, right? 70% is within, or 60% is within 1SD, right? 95% between 2SD, right? 99% within 3SD. This is the rule of the thumb, right? So that means that we can use the idea, just look at the sample mean go left or right, whoops, by 2 SD or 3 SD, okay, that will be the goal to go. Okay, we will be more precise later how we get this number, because this number 2 or 3 or 1.6 or 1.98, as I said, depends on how likely you want to be included, right? Of course, if you want the probability to include the mu is higher, of course you get a wider, right? Just remember, probably you would go to see things, right? If you want to get a fish, right? Then either you can use a fishing rock to get one fish, right? But if you want to be more efficient, right, what we're going to do is use a bowl, a towel bowl, a big net, and grab all the fish together, right? Or you can think, right, I use a gun, right, to attack, I hit 1 point, right? But if I want to get an area attack, I use a bazooka or an atomic bomb, boom, then I just get everything, right? So that's the idea. Okay, interval estimate. So I will get more precise later after the break. So let's a break of 15 minutes. We'll resume at 10:30. Okay, and in the meantime, let's have a you reply. Okay. Hi. I'm back. So, let's see. I mean, just to remind you, next Wednesday we don't have class because that will be rescheduled to B.B.A lab class, which is optional because I can't find a time that satisfies everyone. So, but if you like to attend, you don't have to attend, then it's okay. Probably as the last time I will schedule 2 sections. So maybe Wednesday or Thursday or Tuesday, Wednesday, and then that 2 days, and you can attend either. You don't have to attend all, but because both are the similar. But let's see. So very good question here. Okay, all distribution with n30 follow normal. It's not exactly, but you can say so because usually what we learn is like that. But say uniform n more than 30. I mean, I guess what it means the sample. I guess what it means the sample mean, right? Sample mean from any distribution. When n is more than 30 follow normal, this is the central limit theorem. Okay, and yes, if you think that, I mean, the class more than 30, central limit theorem usually apply, and that would be that the sample mean you can calculate. You can do that as we learn, right? 1 SD, 2 SD is within 70%, right? And 95% within 2 SD, right? If you're above 2 SD, then already you should get A, right? That is something I would you can do that, okay? But I have to remind you that is sample mean, right? It's not exactly your rank, right? So have to be slightly, I mean, in general, that's the case, right? But not this need, the first one need not be true, okay? Because if the underlying distribution is not normal, this is wrong, right? Just have, I think I have to be a little bit more careful here, right? So if the underlying is whatever, okay, even though you take n 100, n is 100 student, give you the mu, give you the sigma, doesn't tell you anything, okay? Central limit applies to sample mean, okay? The sample mean may be bell curve, okay? If you want to, and what we said is if we have normal with binomial with big N is the case. If you think binomial fit your case, then yes. If exponential fit your case, you think Poisson fit your case, then yes. But I'm not sure this for the class distribution, this usually fit. Okay. Usually if I mean, in my experience, usually the class looks like this. Looks like by module. Say some people get 100, okay, and some people maybe say 50 something here. There's some people always I mean, there's some peak over here, small peak over here, not attending any class or some of the class and don't do assignment, and the majority here is like 70%, 70 marks, right? And this is basically most of the people. I think at least 30 to 40% people are here, and the 60% here. So this is what I, and remaining 10% like here. Okay? Usually this is what I learned from the historical data. I mean, from what I taught, and I think this also fit whatever you see in many schools. I think it's similar for CHK as well. But anyway, the statement is not, I mean, I have to emphasize the statement is not exactly true. Okay? Be careful. I mean, you have to make some assumption it's normal. If not normal, it's not the case. Right? Suppose it's uniform. I mean, that will be slightly different. Okay? Because if that's the case, then why we need to study statistics? Right? If this is always true, then we don't need to do anything, right? Just that, then we're done, right? The z-score only apply if a normal. Okay. Thank you. I hope it's clear. T-table, how to look. I will talk about that again today because we'll use T-table. Okay, don't worry, we'll talk about T-table today again. I will do that again. So don't worry. Okay, everyone knows and yeah, we have almost consensus of the weather. That's good. The speed of lecture is appropriate. That's okay. And most of you can follow. I mean, although some of you may think you need some more time, but I hope today is okay. We just give you the reason why we use X bar, sigma square, and then we'll talk about how to estimate interval. Okay. And well, that's a good joke. What am I studying? Let's see, what am I studying? Oh, statistics. Yeah, it's very sad. That's true. Oh, that's a good one. That's a nice joke. My life is a joke. Study just like bad debt. But that accounting will be 0 out every year. But mine is keep increasing. Yes or no? I mean, I don't think accounting bad debt is out every year, but you have to get it to somewhere, right? The bad debt have to go into liability or go to the equity, right? Someone have to get it, right? I mean, sorry for my accounting, maybe I'm wrong, but I guess if you have, then you have to go to somewhere, the balance sheet, right? Have to go somewhere. Even if you cancel the bad debt, you have to cut out the liability or equity. Either equity have to suffer anyway. So I don't see you would be I mean, her balance sheet, her balance, right? Cannot just 0 out. But I think you are right. Study is like it's increasingly hard. As we can see, you guys have a much harder time than I do because of the AI, and then the return of study is decreasing for sure. And I don't complain because actually I am much more difficult than my previous generation, right? The older generation is much more easier than I do. And you will be more difficult than I am. So your son and daughter may be easier, unfortunately, because AI comes out and then they will be even happier. But for your generation, it will be very hard. So maybe probably you guys are the hardest. As an economist, I would guess you guys are most hardest for all, okay, since the modern age. But anyway, sorry about that. But life is tough. I mean, there's no fair, but we do understand that. But what can we do, right? As economists, right? You can just do the best what we have. So anyway, let's go back to statistics. Unfortunately, I can't solve the problem. So let's go to here. Okay, I will be a little bit slower. Okay, so just go remind you. Oh, I think I have a slight typo in the previous one. I should be a square root because SD, right? So it's SD, but I will be slightly. The slide will be correct. Okay. So just to remind you that this guy's a random variable. Okay, and they will be normal distributed with this. Okay. So the question, as we have said, okay, we want to at the symmetric interval about X bar, because X bar is a good estimate of mu. Okay, we want to just not estimate one part, but we extend longer. We want to have a high probability, okay, that X bar actually include mu. Right? Remember, mu is not random variable. The random variable is X bar. Okay, so that is a very important conceptual one thing that you have to remember, okay? And we can show, actually it's not surprising, M will be just Z of alpha over 2 sigma root n. So what is actually the Z alpha over 2 means, okay? Just this guy. Okay. And you see alpha over 2 means this. This is Z, right? 0 is here, okay? And here is 1 minus alpha, and both sides is alpha over 2. I may use other color, right? This is alpha over 2, and this blue is alpha over 2 because symmetric. So this number is Z negative Z alpha over 2, and this number is Z. Actually, this is similar to the T table we do last time, but we will be more clear later. Okay, so this is Z alpha 2. So if you still recall, right, 68%, if this is alpha is 1 minus alpha is 68, right? This is 1, right? And 2 is 95 points, around 95, right? And 3, right? If this is 3, this is going to be 99, right? But we'll get more precise, okay? So this is the main result, okay? You just, the estimate will be X bar, go left and right, by how much is this one, okay? We'll go to the, this is the result, but I will try to convince you this is the right result, okay? That is the, is that okay? I move to other page, okay? Is that okay? So I will try to convince you this is the right result. So this is the result first. I will try to convince you this is right. Usually we call, this is called the margin of error. Right? This is called margin of error, ME. And because you go left by M, right by M, or ME, this is called the width. Okay? And just terminology. The upper bound is called UCL. The lower bound is called LCL. Okay? Lower confidence limit and upper confidence limit. So that is what it means. Okay? There's nothing new, but just terminology. Okay? I will try to justify why this is reasonable. Okay? But this is the result. This is the result you need to remember. Okay? And we'll use it very often. This is the one that we always use this guy for our class. Okay? Almost always. Okay? Now, if this is okay, I justify why this is true. Okay, I'm not going to do the proof, but instead I'm trying to do graphically. Okay, the proof is very simple. Okay, but the idea is also a little bit tricky. So try to pay attention if you can, but if not, that's okay, because so we have by central limit theorem, that is the case, right? And remember, okay, by normal, okay, it means that before you do any sampling, okay, if we want this to be 1 minus alpha, because bell curve, right? The bell curve. Okay. Maybe 1 minus alpha is like 90% usually, or 95, or 99. This is the three number that everybody use. 90%, 95, or 99. Okay. And this number will be mu plus Z alpha over 2 sigma over n, right? So this is what you learn from the normal distribution, right? If you do the assignment, then you know this is what it is, right? Just, right, because if you still remember why this is true, it's here, right? If you convert it to Z, right? This will be 0, right? And this number, if we want 1 minus alpha here, right? This is Z alpha over 2. This is negative Z alpha over 2, right? So that's what we learned, okay? Is that okay? So what is Z alpha over 2 is not something complicated, right? It's just F of alpha over 2. Sorry. F of 1 minus alpha over 2, right? Because the area on the left of this is alpha over 2 is here, 1 minus alpha. Okay. So basically this Z alpha 2 is the tail area, not the left hand side, but the right hand side. Okay. So the Z alpha over 2 is the right hand side alpha over 2. Okay. So that is the notation. Is that clear? It's not the left hand tail, but the right hand tail. Okay, it's the F of 1 minus alpha over 2. Okay. Now, remember 1 minus alpha probability is within this guy. Say 90% is within this guy, right? And how we go back to why we have the X bar plus minus the same thing is fine. The reason is being, the idea is, okay, the X bar may be here, right? Right? And if I construct the same distance, this is distance M, right? I go to M and I go to M, right? And in this case, this will include the mu, right? Is that clear? If X bar is within this range, okay, and X bar extend the hand, same length, it will include mu, right? Because if I touch you, then you touch me. Let me repeat the statement here. Mu, I don't know where, okay? And mu, I extend the distance by M. Okay, M, I know the distance because I know sigma. Okay, I have, hypothetically, I have extend this hand. Okay, and if X bar is actually within this range, okay, and extend the hands, you include the mu, right? Because if I extend the distance here, I touch you and you touch me, right? So as long as X bar fall within this area, you construct this, you include that, right? And here is a high probability is within here, right? So if you do this procedure, that means that high probability, the interval will include mu. Is that clear? So a little bit convoluted. Let me explain once more because it's not easy to understand because it took me quite a while to understand, but maybe you're fast, but okay. So the idea is the following, okay? We only know how the X bar is distributed, right? There's no uncertainty about the mu, okay? Mu is there, but you just don't know, okay? But you would know, okay, before you do any sampling, if I go mu by M by right and left, okay? M is this guy, right? M left and right, okay? And that means that 95% or 90% is fall within here, our point estimate, X bar, right? And but if you extend the same distance M from X bar, okay, and as long as X bar fall within this range, okay, the hand will include mu, right? As long as your X bar is fall within this, you extend the hand, we include this, right? Because I touch you, you touch me, right? The hand is same. Is that clear? So if, of course, if outside X bar is outside not, right? But anyway, there is a high probability within here, right? So that's why when we construct from here using the same length, it will include the mu. That's the main idea. Okay? If you get it, it's okay, it's good. If you don't get it, it's fine. Because this is just a mechanical procedure. Okay, just like accounting rule. If you understand, good. Don't understand, yeah, it's okay, just apply. Okay. But I hope I convey the message why it's true. But of course, for those of you who would be more comfortable with math, you can see the math here, the math there. The math is not complicated. Okay, just two, I think 3 pages of slide. Okay, so you can actually go over the proof step by step. It's not complicated. Okay, but I'm not going to bother you. So now we go to an example. That is something you need to follow. You will be following it in the assignment. Okay, it's the following. We have the standard deviation. We know it's 4. Okay, we'll talk about immediately later soon. But when we don't know this guy. Okay, suppose we know this guy. Okay, and there are ways to estimate this guy. But anyway, suppose we know this guy is sigma is 4. Okay, and then what we know here is the sample size is 64. Sample mean is 3. Okay, this comes on a sample. Now, remember, if we want to estimate mu, okay, if we want point estimate, then we are done. Just 3. 3 is 3, then there's no more. End of the story, right? Because sample mean is a good estimator, good point estimator for mu. Okay, then we're done. Nothing to be done more. But since we want a little bit more, okay, we want an interval estimate. Okay, and if you remember the formula, it's just this guy. Plus minus z alpha over 2 sigma over root n. So this is just the formula. We just apply this formula. Okay. And remember interval estimate, we start with our point estimate, right? That's 3. And how do we do about that? Right? This is actually 4, then we're done, right? And this is 64, right? That's 64, right? What is left is this guy. What this guy is, remember, we want a high probability inside, right? That is what we want is, this is 1 minus alpha, okay? Now alpha, this is 95%, right? So alpha is 5% or 0.05, right? And it's symmetric, right? So this is either 0.025, this is 0.025, right? Right? So if you look at the Z table, right? So this is what? This is 97.975, right? So it's just F 97.5, right? Look at the Z table. Okay, let me check it with you. How to get it 9.975 together? Of course, you can check the Z table quickly. So let me check quickly here. I think the random variable here, right? 0.975. Oh, it's not. Let's go quickly. This one. 0.975. Look at positive. Okay. 0.975 is 0.975 here. It's 1.96, right? 0.975. Because we have to read from area read to the number, so we just read the number here. Go back. 1.96. Okay. Or if you where I am. Yes. Okay. So 1.96. And probably you would ask how to do it in, remember, right? How to do it in Excel, right? We have here 0.975. Okay. How to Excel is just norm inward norm S norm dot standard normal inward 0.975. Okay. Let me show you. S is a standard normal. So let me show you the Excel. Because you want to read the number back to the rows, right? So just use the S inverse. So just very simple. For 975 here, I will just norm dot S inverse. Sorry. For 975. So that's the answer. Okay. So if you want to, this is the number that you read. Okay. Is that clear? So then you just remember the formula. Just put that in 1.96 multiplied by sigma over root n, then you're done. Okay. So it's very procedural, right? I want to ask how to have a 95% confidence. You just apply it. Okay. And almost most of the time is 95%. Okay. Occasionally is 90%. Some occasions 99, but 95 is the most common one. Okay. You ask me why 5? No, I don't know. Maybe give me 5. I don't know. There's some reason. 5 is something. It's common there. Okay. And of course, you would, as I said, you would be wondering, in the real world scenario, we don't have sigma. Okay. We don't have sigma, right? I mean, of course, there's some estimate of sigma, right? But usually we don't know. How do we approach that? Okay. The way to approach that is what we call, you use a T. Just very simple. Just actually from the last class. So you replace this by S by sigma square, that we have T distribution. Okay. So the formula is actually very straightforward. So this guy. Just change Z to T. And of course, T would depend on what the sample size you use. Okay. So there's only 2 things. And so, right, you use the S here instead of S squared, right? Before it's S squared, right? And this guy was Z, right? Okay. The only difference, right? But remember, T has many tables, depend on N. Okay, I'll talk about how to look at the table. Okay, but it shouldn't be difficult. Okay. So let us do example, then you will see how we operationalize that, because that is the only important thing. Okay. This is the important thing here. Okay. Remember, okay, one of the assumption extra we need to make is assume the underlying is normal. Otherwise, that nothing applies. Okay. If underlying is normal, then it's easy. Okay. We can use T. And consider the case we have n equal to 20, sample mean is 3, and sample variance 12. Okay. And from the data here already, we know our best guess for mu is 3. Our best guess for sigma square will be 12. Okay. That's already we know. If I give you data, you collect it, calculate sample mean, sample variance, you have a good guess on mu and sigma square. Okay. That's already there. And we go a little bit further. Can we get a better estimate for mu, right? Give me an interval, how to get the mu, okay? And the operation is that, right? Remember, x bar plus minus Tn minus 1 alpha over 2 S over root n. So this is the formula that you always remember. So you can say, I can just write that down, right? Because I remember that formula. Of course, you can look at the slides when you do assignment or the test. But this is the formula that absolutely you will need it. Okay. And we know already most of the answer. Okay. We know this guy is 3. This guy is 12. This guy is root 20 because n is 20. Okay. What's left this guy? Okay. And we need to be slightly more careful, right? T is like this, right? It's a bell. It's a bell. Again, it's 0 bell. It's not almost the same, right? Again, we want in the middle, right? It's 1 minus alpha, right? So that is the thing. In the middle, we want 1 minus alpha, right? Because 95%, right? So we want this is 95% for 95, right? And that means that the both sides are 2.5. I hope that shouldn't be a difficult thing. 0.025, right? Because middle is 95%, overall 100%, right? So both sides 5%, right? Is that clear? So basically, what I want is from this point, I go back, I want a 9.975. All right? That is what I want. All right? And what is this number? It's simply given from Excel function. It's called T dot inverse 0.975. And you have to put n minus 1. N is 20, so 19. So this would be the Excel function that gives me close to 2. Okay, you can see that is one is 1.96. This one is around 2. So basically, usually that's why the rule of thumb is 2. Usually we say 2 SE. Then that's why they always said 2 standard error plus minus, right? Okay, and probably some of you ask, okay, how can you read this from the T table? Okay, and you will see why I use this graph, and that's why you learn the T table is look like exactly as what we have seen here. Okay, if you remember the T table, from the last class, looks like this. Okay, and this is exactly what we want, right? It's already cater for confidence interval, right? How do we do it? Remember, go to 19. Okay, actually this table is T inverse table, right? Table 19. I want the area to be 95, right? So 1 minus alpha, right? 95, right? So basically look at this column. Most of the time you look at this column because sorry, this is yeah, because 95 in the middle, right? So 95 then is 5% what's left, right? So basically this guy. This number. Is that clear? Yes. Okay. Is that clear? Just go back. I do the Excel, right? For 975 and T dot inward. Okay. And 19. So the same answer. Okay. So that would be the way to do, right? Basically, this is the number usually you do, right? The only thing you have to be careful is for T is n minus 1 or n. So that's a little bit tricky part, but once you do the assignment several times, then you will be remember just accounting rule, I always say, right? So whenever you want to a confidence interval for the mean, this plug in the formula. If you know the sigma, plug the Z formula. If you don't know, you plug the T formula. Okay, that's it. And the reason we explained already, right? Because you know how X bar would look like, right? So just apply the same thing. Is that clear? Is it too fast? So there's nothing new here. Okay. I don't want to there's something to talk, but I don't want to talk, but before we end, I want to give you a little bit philosophical question, philosophical explanation a little bit on this one. Okay. And there's a okay, let me finish this one first. So for proportion to be same. Okay. The same thing applies. There's no difference. Okay, because that the only difference about proportion is we don't need to worry about the sample variance, right? Because the sample mean actually gives us what we want. Okay, so this is for sample final data. It's always this formula. Same, right? Just use the thing that we know, the bell. Okay, and we can go over that. Okay, so let me finish the example, then probably we can end today. So we have n is 64, sample proportion is 25. So then if we want to estimate the population proportion, then we're done. That's done, right? If we want to estimate the population variance, we are done, right? It will just 0.25, right? Times 1 minus 0.25. That will be our estimate of variance. Although it's biased, but we're done, right? And if we want an interval estimate, we want a confidence interval, 95%. How are we going to do that? Very simple. We just P plus minus Z over 2. That's the formula, right? P 1 minus P over N, right? And for P, you know already, right? For P, you know already. P, you know already. This you know, this you know, this you know, this you also know, right? Just to remind you how to do this is we want this to be 95%. Okay, that means that both sides is 0.025. Okay, or it means that up to here is 0.975. Okay, so Excel will be just very simple. Normal, standard normal, inverse 0.975. That's the answer. But anyway, you should remember this 1.96. Okay, or close to 2 anyway. So just plug in all the number, then we're done. So we're mechanical. Okay, they're mechanical because you know the logic already. Okay? I hope you understand logic, but otherwise it's very mechanical. Okay, I guess I should more or less end here, but I just maybe we can end 2 minutes earlier today because sometime overrun, but I hope this is okay. So basically, today you learn a lot of stuff because you learn point estimate, interval estimate. Okay, and next class we talk about hypothesis testing. Okay, so I think I will try to give the assignment, put it on there. But yes, okay. So I see you next Wednesday. Sorry, next Friday. So Wednesday no class. Okay, we will schedule for other day.